This video clip is to introduce the Insight L700 system and its user interface, and it describes the system's potential to deliver enhanced safety, reliability, and efficiency to the distribution network. Just a recap of AIQ, it is the outcome of a collaboration between leading engineers in the European power industry, and the Insight range of products and software is the result of this collaboration. The solutions we deliver have been designed to enhance the networks in the face of major changes, with, for example, the onset of distributed generation. As part of the design process, AIQ has developed high earth fault sensitivity of better than 10 kiloohms, supported by synchronized data of better than 1 microsecond resolution, all packaged in robust and reliable product designs. Our technologies deliver the major enhancements needed to address the safety, reliability, and efficiency of the networks, with a focus on improved safety. So let's get into the L700 system and see what it does. In order to understand the L700, we will first look at the overall architecture of the system. The L700 consists of a network of substation installed sensitive earth fault and voltage measuring devices called S700s with distributed line mounted sensors. The line sensors communicate to their local data concentrator via short range radio, delivering fault and disturbance current activity, including sequence values of current. All data measured in the substation or at the distributed nodes is time synchronized to the GPS clock to within 1 microsecond, making the entire system data time coherent. All deployed devices communicate via 4G, 5G to a dedicated secure server that hosts the master system software. Within seconds, fault activity is communicated to operators via SCADA, smartphone, and email, detailing the fault in terms of what, when, and where it was. For security, the data is end-to-end encrypted. For equipment deployment, an S700 is installed for each individual feeder in the substation, with current inputs via clip-on CTs. In addition to fault location, the high sensitivity of the S700 supports protection. This graphic shows that the triplets of sensors or nodes communicate via their local L700 to the server. These nodes are deployed throughout the network, and each node has 3 wireless CTs that sample current at 64 samples per cycle. Each line sensor communicates by short-range radio to its local L700 and then forwards the data to the master software for processing. Peripheral devices may be plugged into the L700, such as traveling wave modules for more accurate distance to fault values and wireless range extenders. The number of line nodes installed per feeder is dependent on how critical the line is and its impact on SAIDI and SAIFI. But as a general rule of thumb, and with the support of DTF values, 3 nodes per feeder is the normal protocol, thereby dividing the line into 4 sections. The L700 is further enhanced by the M710, which is a handheld device used to manually navigate the operator to the actual fault site. Now let's look at the GUI itself. This is the home page of the master station software. The column on the left is a list of fault records showing the date and time of occurrence of fault, the substation, the faulted feeder, and the faulted section. On the right is a list of alarms from the devices, and at the bottom are fault statistics for the network being monitored. The middle shows a model of a 20 kV network in East Anglia, UK, which we use for the purposes of fault simulation and demonstration. It consists of 3 substations and 5 feeders that are all interconnected by tie switches which are open. The positions of the substations, Thresher, Goosham and Holton, together with their feeders and nodes, can all be shown on the Google map. Let us examine one of the simulated faults, which is fault 2 on the feeder C from substation Thresher, which is an isolated neutral treatment. The fault was between nodes 2 and 3, and this is clearly shown on the Google map with the flashing faulted section. By clicking the network button, the faulted section is also flashing in the network diagram. If we drill more deeply by looking at the waveforms from each node, starting with the first node, we first look at the 3-phase and 0 sequence current, magnitude and phase, and then at the transient waveforms. By moving the cursor to the fault positions, we can see that the zero sequence fault current is very small at 5 amps, and its angle of 1 degree is in phase with the A phase current. The transient waveform also shows the small fault current magnitude and the angle relationship. If we look at node 2, we see the similar magnitude and phase and the transient waveform as the first node. Looking then at node 3, the magnitude and phase of the fault current, we can see that the zero sequence current angle is 162 degrees with respect to A phase current and is antiphase as compared to those at nodes 1 and 2. This is also shown in the transient waveform. By clicking on the View Details button, the waveforms from all the nodes can be seen, with the zero sequence currents of nodes 1 and 2 which are in phase, and in node 3 which are antiphase. Because of the time synchronicity between the nodes, the master station is able to time align all the measurements and waveforms from different nodes on the same time axis, thus providing accurate fault localization of the faulted section. So thank you for your time. And if we can be of any service to you, please do not hesitate to contact us or visit the Ask the Expert section of our website with any queries you may have.